Well, hello again, everybody. Um, Welcome to DSC DACH tech tutorials. Our first tech tutorial for today will be Stanko Kuveljic. He is head of machine learning engineering at SmartCat, and he will tell us more about building a simple RAG application from fundamentals to implementation. I hope you will enjoy, well, I'm sure you will enjoy next hour and a half with Stanko, so I will give my word to Stanko.
Thanks. Hello, everyone, and welcome to this tutorial. Today, we'll try to do something different, right? I would like to quickly go through some fundamentals on how to build the RAG and to build it from scratch. All of these code examples, we won't use any frameworks, just an OpenAI and Pinecone as a vector database. My goal is to go through it quickly, to do a speed run of it, because you can find similar tutorials anywhere on the internet, and it is pretty much easy to create a RAG system, but it is quite hard to create a good RAG system. So after we go through the code that builds a simple RAG system, I prepared a few hands-on exercises for everyone. And to be honest, I didn't solve them in advance. And to be honest, we probably won't make it to code everything today. But the goal is to spark discussion and to collaborate on solving the tasks for at the end of the session. So we can start. I hope every one of you used the Colab. It's like a Jupyter notebook where we can run the code, and you can go to the Colab by typing Google Colab on a Google search, or maybe I can share. Okay, and for this session, we are going to use this notebook that I prepared. I will share that in chat so you can open it. Did everyone receive the links that I provided? Maybe if I could get from the support confirmation.
I think, I'm not sure, I think you sent your message just to hosts and panelists. In the chat, you can change to then everyone, and then they will be able to see it.
Okay, just let me try that again. Seems like that I can't change it to everyone, just to the support and the host and panelist.
Okay. For now, I'm going to send the link for everybody. And in the meantime, I'll figure that out.
Okay.
Okay, I would just like for some attendees to raise their hand if they got a link. Okay, perfect.
Okay, great. We can continue then. You can just copy this URL up here and in the file, open notebook. You can select the GitHub. Paste the URL and press enter. It should open up a notebook that we just shared. Okay. Yeah. For today, we want to build a simple RAG application and to see what are steps and what are stages in the RAG application that could answer questions based on our private data. Objectives: to cover RAG fundamentals, to set up and use Pinecone DB, and in the end to implement the RAG application. But as I have said at the beginning, we will cover it, I hope, quickly, so we can focus on the hands-on activities and to start play with the RAG and see what types of question works, what types of question doesn't work, and what are other advanced techniques that we can use in our system. First, we can just, if you haven't used the Jupyter before, you can execute cell by clicking this play button here or pressing Shift Enter. You can just run, and you need to wait for a couple of moments to connect to a free CPU instance. For this session, we don't need a GPU because we are just relying on the external services for the ChatGPT and so on. For this session, we need a couple libraries like OpenAI for calling LLM ChatGPT. We need a Pinecone client with gRPC support to speed up the upserting time. And we need two libraries to process the data set that we are going to use in this session. You'll probably get an error here, but everything should work. Libraries should be installed, and we can continue to the next cell. The next cell is just a boilerplate code to visualize the results that we are going to see in this session, so we can completely skip this cell and just execute it. It will just create a HTML and the Markdown to visualize everything better. Okay, let's step away from the RAG for a moment and see why do we even need the RAG, right? I hope every one of you used LLMs before, at least chat with ChatGPT. And what you might have noticed is there are some problems with it, right? And these problems are slowly reducing by releasing a newer model, by releasing a better models, and so on and so on. But there are some cases where using a simple, a plain LLMs are not enough. And let's go and see what are these use cases. First, we need to set up an OpenAI API key. I will again paste it to the chat and OpenAI key that we are going to use in this session. If support could paste this key in the chat so everyone can use it. Okay, great. You can just copy this key, execute this cell, and it will open up a prompt where you can just paste the key. Okay, now we can execute the next cell. The next cell is just a wrapper code that calls LLM. We call that function generate. We'll see why. Prompt that we want to pass to the LLM and ask a question. OpenAI client that we just created using the OpenAI key, and a model name that we are going to use in this session. In this session, we are going to use GPT 3.5 Turbo to enhance the downsides that plain LLMs has, but to mention that with the larger models, with the latest model, these issues are still there, but in reduced fashion. Okay, and here we are just using OpenAI client to call GPT with this model, and we are sending some history of our messages with our prompt, and we just return the message. More information you can find on this URL here. So if we execute the cell where we ask what is the capital of Germany, we will get a right answer, right? The capital of Germany is Berlin. So far, so good. But what are all these problems that LLMs have? One of the problem is that their informations are unchecked. They are trained on the vast data set and all over the internet, but they don't have the ability to say what is real and what is not. And if we ask an LLM who is the 25th person that landed on the moon, it won't tell that there is no that person, but it starts to hallucinate. So one of the problems of LLMs that they're prone to hallucinations. Of course, latest model are better at handling that, but still there is a there is a problem when we ask for something and we can't be completely sure if that information is correct. Here, we do know, but imagine your data, your financial data, or your hundreds of PDFs, and you ask a question about it, and it doesn't, and it starts to create answers that doesn't exist. They are not validated, right? That could be a potential issue. Now, I would like to cover another problem. Besides the hallucination, it is a knowledge cutoff. What do I mean by knowledge cutoff? So LLMs are trained on the data like any other ML algorithm, right? And GPT is concretely this GPT 3.5 is trained on the data available until 2023 and October, I think. And all the information, all the happenings, all the things happened after that point in time are unknown to the GPT. And let's see on this example. If we ask, I hope every one of you know what is Mistral. Mistral is LLM released, I think, late last year or early this year. I'm not sure, but it is something that GPT 3.5 doesn't have knowledge about it. It happened after the cutoff. So if we execute this cell, we will get the results, right? It won't tell us I don't know, and it'll probably start to hallucinate. In this example, it told us about a sailboat, and I googled this answer, and there is a sailboat called Mistral 7B. Mistral, not 7B. And because this happened before, after the cutoff, LLM doesn't have an idea about it. So you can imagine what are consequences of this. LLMs are also trained on the publicly available data, I hope. And you, in your organizations, you have vast data sets that are not publicly available on the internet. So if we want to use LLM for your use cases, where you have a bunch of PDFs, a bunch of documentation, bunch of some internal procedures or whatever, and if you want to use an LLM for it, you can't use some that is trained, because that is trained open source data, because there is no knowledge about your data. And this is one of the reasons we need a RAG system. Imagine imagine the scenario. What if we feed the GPT with the context? What if we have a way to explain the GPT what is Mistral 7B, and then ask it to return us an answer based on our question? What if we could potentially type to the LLM some summary of the Mistral paper and ask it a question: what are key benefits of a Mistral 7B? And if we have something like this, LLM will work, right? It won't hallucinate in that frequency, and LLMs are good in summarization, in reasoning, in the extracting some useful data out of the context. This is exactly what we need to create a RAG. We need to find a way to provide LLM with enough knowledge with our data and ask a question about it. Okay, let's recap why we need RAG. We will enhance the accuracy of the results. There is a less possibility for hallucinations. Although hallucinations might happen, they're greatly reduced. It is not cost efficient to constantly fine-tune your model, your LLM, with the fresh data. And if there is a knowledge-intensive task where your documents might change every day or every minute or so, if your knowledge base is growing constantly, it might not be efficient to have an LLM handling this, fine-tuning it on your data each and every time. So RAG is something that could help us with that. Of course, there are now large context LLMs that could potentially overcome the need of a RAG of the RAGs, but they have also problems such as hallucinations, and they're slow to answer. And there are some papers. From my experience, using a less context provided me better answers. And last, one of the reasons we need RAG, we can do a fact checking. We can say, hey, this is the context, this is the question, this is the answer. I constructed the answer out of these facts from these documents that you have. And this is something that can greatly help with debugging and explainability, and it will give credibility to our RAG system. Now, how to build a RAG? For building a RAG system, we need 3 things. We need to build our knowledge base. We need to construct a knowledge base in that way. So the second thing we need, a retrieval, is quick, accurate, and efficient. The third thing that we need is to take the take the results from the retrieval, construct the context out of the retrieval results, and generate the answer on our question. RAG, Retrieval-Augmented Generation. We need to retrieve the relevant data to our question, to augment the context of the LLM, and to generate the answer using the LLM. This is basically it. So let's start with the first one, how to build a knowledge base. I assume every one of you heard about Pinecone. Pinecone is a vector database that is efficient for the retrieval and scalable. But before we arrive to the Pinecone, let's see how to build a knowledge base. First, we need a bunch of documents, right? We need to parse these documents, to load it, clean it, to separate it into meaningful pieces. And we need to encode it. What does it mean? It means we are taking a part of the document and we are transforming it to a vector. And we call that vector embeddings. So what is this vector? This vector is something that, imagine it like a compressed version of your piece of document that carries the semantic and the context. Vectors are built in that way. So if you have two documents that are similar, semantically similar, then these two documents will have vectors that are also similar by some similarity metric. And with that assumption, we can place these documents together, and by using a vector similarity, we can retrieve the relevant documents based on our question. That is the assumption. Now, we need a way to do this quickly, to go through all vectors and find the top 10, top 20, or so on, that are top similar to our question. This is where we need a vector database. And let's see it here. We have a content. These are our documents. We have an embedding model. In this session, we are going to use an OpenAI embedding model. We will get a vector. And we store these vectors into vector database. Now, when we ask for a question, this question goes to the embedding model. We will get a vector. And based on the vector similarity inside vector database, we will return the results, which are top K elements, documents that are most similar to our question. Now, the next thing would be to set up a free Pinecone account and to start populating it with data. We can execute this cell here, but before that, we will need a Pinecone API key. You can obtain a Pinecone API key by going to the Pinecone website, and you can do a sign up. Type your email. And in a few moments, you will receive the code that you need to paste it here. And it will log you in. Probably you'll get some questionnaire regarding the if you are first time opening up account, you will get a questionnaire about how you're going to use a Pinecone and so on and so on. You can skip that, I think, and you will get something you will get a dashboard like this here. API keys, you can find them here, and you can show them, copy them, and this is everything we need from a Pinecone, just an API key. If you already have an API key, great. You don't need to follow these steps. You just need an API key from the Pinecone. Now we can execute this code, and in the prompt here, you need to paste your Pinecone key. And press enter. I'll wait for a couple of moments for everyone. Now, if you have any questions regarding the progress so far, please don't hesitate to write it down. I'll occasionally see the Q&A chat, and I'll try to answer. So here we need to use US East 1 region because this is for starter tier of a Pinecone if you are using a free version. Cloud, it is AWS. Index name that we are going to use in this session. You can call it whatever you like. Vector dimensions is this. And it is about it is the size of a vector from the OpenAI embedding model that we are going to use in this session. Once we execute this cell, we need to initialize our Pinecone client. We do that by importing Pinecone gRPC, and we are passing our Pinecone API key here. In the end, our client will just list all the indexes we have. If you just started, if your account is new, you will see the empty list here. And if you used Pinecone before, you will see one of your indexes before that you created. And that's it. Now, we need to create our index that we are going to populate with our data. I still didn't tell you about what data are we going to use, but right now it is not important. It will be important in a few moments. How to create an index. You can find more information on the Pinecone documentation, but for now, we'll first check if our index name is present in the indexes. If it is, then we will remove it. So make sure that if you're having already Pinecone account, that you don't use the index name that you already have, because it will be deleted. And it's simple. We are using a Pinecone client to create an index with index name, vector dimensions that we provided, cosine similarity as a similarity metric that we want to compare vectors, and we will going to use a serverless Pinecone index. Serverless is something relatively new, and they are more optimized and more scalable and cheaper. This is not the scope of this tutorial, but for more information, you can find it here. Basically, what Pinecone did is they separated the storage from the compute and get better scalability. In the end, we just need a reference to our index using pinecone.index. We execute this cell. And this means that we successfully created our index. Now, we are moving to the data set. In this session, we are going to use a data set of a sample of AI papers released in some point in time. And this data set is already prepared, so we don't waste our time on parsing PDFs, creating chunks out of it, calling the embeddings, and so on and so on, because it will take us time. It is a science for itself. And just assume that we have everything clean and prepared. This data set, you can find it on the Hugging Face, and this is just a subsample from another data set that contains much more AI papers. We can load it, and it will download for us. Now that is done, we can display and see what is it inside the data set. Okay, so we have a title, we have some IDs, we have the text of the chunk that is part of the paper. We have a paper summary and a link to original paper and some other metadata like categories, the date when it's published, and authors, and so on and on. We also have two more fields One is embeddings. And if we execute an SL, we will see that each row in this data set contains a vector with 1536 dimensions, and there is also another field called metadata. And metadata is just a dictionary that we are going to pass into Pinecone, so we have more granular filtering. And this metadata is just these fields from the data set put together. To cover quickly what has been done with the data set. So we have AI paper, which is in PDF or whatever format. We splitted this paper into some chunks. And why we are splitting paper into chunks? Because we want to create embeddings. And these embeddings are sensitive. They are sensitive if you provided too many, too large text. It might lose some important information because they are compressed version of a document. And we need a good strategy on how to split our text. It could be by counting number of characters, or do some more magic regarding to see the document hierarchy and then split it based on the paragraphs. Or we can do some semantic chunking, or there it is one of the, I would say, one of the most important parts for the retrieval-augmented generation systems is retrieval. You need to retrieve the best data possible, so you get the good answer. And one of the way to improve the quality of the results is by doing by choosing better chunking strategy. And once we have chunks, we encode it using an OpenAI, and then we have each chunk with its own embedding. We upsert it into Pinecone. And this is what we are going to do now. There is you can find all information about upserting the Pinecone here. Basically, it needs triplets. It needs a list of triplets. It needs an ID of a chunk, document, whatever you are embedding. The ID, the vector itself, a list of numbers. And optionally, it needs a metadata. It is a dictionary, as we have seen here. And you can do a filtering by this metadata as well. So I created here a function that just take this data set that we pass, convert it to a pandas, and the index reference from Pinecone has already implemented the efficient way to upsert the data if your data is in pandas format. The pandas data frame for Pinecone just needs 3 columns: ID and embeddings called values, and the metadata field. If we execute this, we can provide the batch size to optimize for throughput of the upsert. And if we execute this first, we will just observe the 500 just to see that it works. Describe the index, and we can see the 500 of vectors is abstracted to Pinecone that we can use. Now that that works, we can execute this line here, and it will start abstracting the whole data set. While it is abstracting, we can revisit what we have done so far. Okay, the first thing that we did, we implemented generation step. We called LLMs, GPT 3.5, and we'll see that it could create answers to our questions. Although these answers are not always great because it hallucinates, it doesn't have the relevant data and so on. The second thing that we did is we set up a Pinecone index, Pinecone account, and we created the index. And the third thing that we've done so far is, and what we are doing right now, we are building a knowledge base out of our AI papers that later we'll see how to search. What are we going to cover next is we still need the retrieval part, which we will call Pinecone to return us chunks of an AI paper that are relevant to our question. The second thing, we will take these relevant chunks and we will create a context out of these chunks to feed it into LLM. And the last thing, we are going to see how it works in action, and we will start then exploring, playing, and create, and we will try to improve the quality of results. So let's continue. This is finished, so we can continue. The second thing, so first thing was building a knowledge base. Now, the second thing that we need to build a RAG is to retrieve against the query. How does it work? So we have an input query. It could be, what are key benefits of a Mistral 7B? This query goes to the same encoder model. We get a vector from it, and we can just call index.query from the Pinecone. That will allow us to search for the top case similar chunks that are similar to our query. So we want to find a chunks that semantically mention in this case, Mistral 7B, with the goal to provide it to LLM to answer us question. So let's see how it works in practice. We have a function called encode. We'll provide some text. The text could be a query. As we have seen so far, it could be what are key benefits of a Mistral 7B. We provided an OpenAI because in this session we are using OpenAI embeddings model text embedding trees mode. And this is simple. We just need to call OpenAI client to create embeddings for our, and we'll just return a bunch that is basically our vector. Let's see how it works. Okay, if we ask a question, what are key benefits of a Mistral 7B? We should get a vector. Yeah, vector with these dimensions. So far, so good. What is in the embedding model for our questions and for our documents? So this must be in sync because of the vectors, of course. We need to know to have the similar vectors for the similar documents and questions. Now that we have an encode function, we need to use that vector to get the results from the Pinecone. We do that in this function called retrieve. The retrieve takes the query, takes the index, Pinecone index that we created, and the OpenAI client, and we say how many examples, how many top most similar results to retrieve from the Pinecone. The first thing we do, we call the encode function that we just created. And then we do a index.query with this embedding top K, and we want to return metadata because we put the text of the chunk inside the metadata, as we'll see now. Okay, and we can execute this line here. What is Mistral 7B? A famous question for this session. It will return a 10 chunks that are most similar to this question, and if we print the top result, we can take a metadata and we can take a text of this chunk. And the text of this chunk, we can see that this is the abstract of the paper. So it works reasonably well. We solved retrieval right now. And what is left is to augment and generate. Let's recap how everything works. User types a question. This question goes to the retrieval that we built. And what does that retrieval do? It encodes our question, calls the knowledge base to retrieve the relevant context, to retrieve the top similar results for our question. And we construct the context for the LLM, and the LLM generator will give us an answer to our question. Now, this is for the most simplest version of the RAG. There are many pieces that enhance the retrieval part, that enhance the generator part, and so on and so on. But on the high level, these are steps. So we are ready to create a final step and to generate the answers based on the context. These are helper functions. We will cover them. Let's focus now on the RAG function. Direct, like we have seen, to retrieve the results for the query index OpenAI client with the top, and to retrieve the top K results. We implemented this function earlier, right? This is what we just implemented. Then we use these query results with the query we provided, and we pass it to augment function. This is this function. The goal of the augment function is to explain to LLM what should it do. It creates a prompt. It creates the prompt where it asks LLM to answer the question based on the following context. And that question we might put up. It's not important, but we put the question inside the prompt, and also we put the context inside this prompt. And we generate context by creating calling another helper function that will just go through the metadata and extract relevant results from the chunk. It will use title, authors, publish when it's published, summary, text of the chunk, which is most important, and source if we want to do some fact checking in the end. Now we created a prompt with the context question. We just need to call the function that we first created. It is called generate with this prompt and OpenAI client. The results are response, and for the debugging purposes, we'll see the retrieval results. We can execute this, and let's see if we improve the results on our what are key benefits of a Mistral 7B. See if everything works correctly. Yeah, it works. So we asked a question, what are key benefits of a Mistral 7B? This question went to the retrieval process to find the papers that could potentially answer this question, right? And we use these chunks, text from the papers, to create a nice prompt. And with that prompt, we ask LLM to provide us an answer. This is a powerful technique, which is relatively fast, and it allows us to enrich LLM with our own private data that LLM never seen before during the training process. Let's see how what information Pinecone retrieved based on this question. The first chunk is retrieved is some information about Mistral 7B, water performance, how it's tuned, and what are some results. The second chunk was the abstract of the paper, so it's reasonably well, right? And based on these two, on the texts like this, and some information out of these chunks, LLM could answer the question. Let's see another example. What is skeleton of thoughts? Skeleton of thoughts is another like chain of thoughts. Skeleton of thoughts is something that it's a prompt engineering strategy. And in this example, same, everything, the process was the same. For this question, we found the top similar results that could potentially answer the question. We took these results, constructed a prompt for LLM, and LLM was able to answer the question and format it for us. There is another example on the use cases for the recommendation engines as well. And we can see that these type of questions are usually well answered by RAG. But as I said in the beginning, it is easy to create a RAG function. It took us less than an hour, and it works okay. It works 60-70% accurate. It's okay, but there is always but. It is quite hard to build a RAG that is good, and I assume that someone in the audience had experience when they started the project. They looked easy. It looked, we can build this very quickly, and it worked okay until it doesn't. Until we realize, hey, we didn't split the text properly. It returns gibberish. It doesn't work well with the tables. We have also images in our data set. We need to count for them. The user types, some unimaginably different questions. And one of these questions is the comparisons. And the context is limited. We are relying on the retrieval process, on the vectors, and we might not retrieve all results at once that we need. And someone could type a question like, write side-by-side summaries between Mistral, Cosmos, Palm, and if there is a key difference between them, what is it? Okay, this is a lot of text. There are some noisy text here, like write side-by-side summaries. And imagine that goes to the encoding model. We create a vector from it, and it will probably put us somewhere in the space of the documents there that is not relevant to our question, right? This is just a filler. And also we need to count for Mistral, Cosmos, Palm, and so on and so on. And if we execute this, it will say, I don't know. Since it doesn't, it couldn't fetch the all results with from the vector DB that are relevant, or it fetched the gibberish. we can always retrieve more data, right? From the vector DB, we can use the larger context out of it, and better LLMs and so on and so on. But this is still a problem. See, there is a question. The question is, how do you go about measuring response accuracy or compare two summaries to select the best? Okay, the evaluation strategies. So far, in my experience, what worked the best are two things. You are using a judge. So this is one thing. You're using a judge, and who is the judge? Usually, you can the first judge could be a different or the same LLM. So basically, you are taking the answer that the first LLM provided. You're passing the question, passing the answer, and passing the whole context. And you can ask the following questions. You can ask, is this the answer of the for the question based on this context? Is this context relevant to the question? How faithful the answer is? Is there something is missing? Is it complete? And you can create your own criterias, and you can just ask another LLM to measure how good is your answer, and you can derive some metric like accuracy or so. The second judge, which could be time consuming, is having a person to look at the answer, and we might call that human in the loop. Let's imagine the assistant that is sitting behind the keyboard, and he or she validates the answers from the LLM and provides a good one. This could be good because if that person provides, hey, this question is okay, this answer is okay, but I would like to see this, and this, right? Then you can use that human provided answers as a labels to measure the accuracy of the results. This is the second approach that you can use. Okay, let's see. Let's continue with the session. As you have seen, we created a RAG, which it works okay, but there are some type of questions where it doesn't work well. How to improve it? First, one of the improvement points could be to understand what are the questions, right? This is one first. These are two first exercises. The first one is to understand if the question is about comparisons, and if it's not, if it's a regular question. Now, I don't know if you guys could join the chat, or I would like to hear your opinions on how would you approach to this problem. So you want to solve this type of the problem where someone write me side by side summaries between Mistral, Cosmos, and Palm, and to point the key differences. This is the first problem. The second problem is similar, but instead of comparisons, we want to focus at some point in time. Remember that we had in the metadata the date of the release of the paper, and we want to use that somehow. And for example, give me all key advancement from the e-commerce search that is after 2022, let's say. And this type of question would be hard for a RAG to answer if it doesn't if you don't retrieve the relevant results. And the third exercise is the re-ranking usage. Why do we need re-ranking, and what is re-ranking? When we talk about the speed and the scalability, we are relying on the vector similarity, which we covered now. And vectors, as we have seen, they lose some information. They lose context. On the other hand, rankers can go a step beyond that. Rankers, on the other side, could look at the query and the context at the same time and decide if that is relevant or not. So what might happen? It might happen that you provide the answer, provide the question, and for that question you might get some similar results, but not relevant to the answer, right? For example, if you ask a question, what is the capital of France? The capital of France question, and the top similar results from the DB, if you rely just on the embeddings, won't be the capital of France is Paris. It will be the same question. It is what is the capital of France? So since we are relying on the similarity, but not on the intent and the context that we want to do, this is why we need re-rankers. And the question is, why don't we use re-rankers in the first place? They are slow. So since they need the question and the context provided at the same time to do a comparison, and they are not doing it in the scalable way. And but on the other side, they're more accurate and could go deeper in determining the relevancy and the context besides the query and the text provided. And with the re-ranker, we can optimize for the result. For example, there are some queries that would be hard for the RAG that we build to answer. For example, what are the best practices for designing prompts in promptable segmentation tasks to maximize model performance on diverse downstream applications? this relates to a paper from the Meta called Segment Everything. But here we don't know about this paper, right? The results would be scattered. It will try to designing prompts, then it will try to look for the model performance on diverse downstream. The results would be gibberish, but in this gibberish, we will get also some relevant answers. But the goal is to reduce the noise for the RAG, to provide the less context, but more quality of context. So the LLM doesn't get confused and could answer our questions with a great quality. Now, we have around 10 minutes. We can start with Q&A maybe. Or I would also like to hear your opinion on how would you solve the exercise 1 or exercise 2. And potentially we can start coding it, but clearly we won't make it on time. So how would you like to proceed?
You can write your answers in Q&A session, right?
Yeah, you can use a Q&A chat to type the opinion on these exercises, or if you have any questions regarding the RAG in this session, we can discuss that. There is a question, will a video of your tutorial be available? I think yes, but support can confirm that.
Yeah, it will be available after some time. We are recording these webinars, so yeah.
Okay, if there are no questions, then we can maybe quickly go on how we could, for example, solve the first exercise. There is a problem with the questions types, right? And in advance, we can limit our users to provide us the questions formatted in some way that we can later use downstream and provide the results. Or we can try to find a way to understand the queries and to extract the relevant data out of it. What does it mean? That means that we can use LLM or any smaller LLM, or maybe we can use some metadata extraction like NER or something like that to first classify our query. We might want to have the classification between, hey, this is a regular query, this is exploratory query. Maybe someone wants to explore, or this could be a summary query where we want to summarize something, or this is a comparison query where there are several things to compare, and based on that information, we can see later that if we have a classification, then we can reroute our system to do something more to improve the results. For example, how would the steps look like? First, there is a query, right? And we can call LLM to classify and extract the data. For example, we could use a prompt like this. Please, for example, classify the query into the following classes. And then we can type, for example, regular, and we can type comparison. And for the regular, we can give an explanation, any other query. That is not comparison, right? We can provide more examples. We can apply a few shot learnings and so on and so on. Comparison, we can, for example, copy this. This is a poor prompt, but I hope you get an idea out of it. Then, if this is the comparison query, please extract the items that are needed to compare. Let's say example query output, and output could be Mistral, Cosmos, right? And then the next part of the prompt could be, hey, I need it into the JSON format, right? And then you can just load it as the JSON into dictionary of Python, and you have more control on the fields that GPT can return you, and so on and so on. But for the sake of this exercise, we won't make it on time. Let's see what we will get if we call generate. Let's see this. I don't have autocomplete for some reason with client. This. Let's see what we get. Query is not defined. We need to provide a query. Let's try the same. It is not defined. Work now. Query is not defined. Okay. What I did. We don't need this one. Okay, so it works. It says its classification is comparison, items to compare Mistral, Cosmos, and Palm. And what would we do afterwards? We can do a separate rags call for Mistral, for Cosmos, for Palm, to provide us the answers, right? For example, it could be a summary. Take me a summary of Mistral, take me a summary of Cosmos, take me a summary of Palm. Or it could be provide me performance, provide me the other types of things that would be good to compare. And then we will get results for the Cosmos, for the Palm, and for the Mistral. And in the end, we can combine these results into another LLM call to provide us what are key differences between these 3 or 4 or 5 or any other comparisons we have. I think we don't have time to continue implementing this, but let it be for your homework. And please let me know if you what are your thoughts about it, and if you have any other opinions on how you would solve this problem. And thank you for this session.
Stanko, thank you for your session. It was really amazing, and I hope all of our entities really enjoyed it. So thank you once again for taking part in DSC DACH this year. And also, we can't wait to see you at the next 2 days of the live conference as well. And for the other participants, we'll have 15-minute break right now, and then we'll proceed with the next webinar after it. Thank you so much for everyone.
Thank you.
Bye-bye.
Bye.